Picture a universe cloaked in perfect darkness, no stars, no galaxies, just an endless sea of empty space. This was the Cosmic Dark Ages, a time when the entire universe was a silent, shadowy void. Then something extraordinary happened. Tiny flickers of light pierced the darkness, the first stars igniting, their radiation tearing through the fog of hydrogen gas like a flame in the night. This was the Cosmic Reionization Era, the moment our universe woke up. But here's the thing, we still don't fully understand how or why it unfolded the way it did. Even with all our telescopes and supercomputers, this epoch remains one of the greatest unsolved puzzles in the history of the cosmos. What triggered this grand awakening? How did those first stars and galaxies carve paths through the darkness, reshaping the universe into the luminous web we see today? And why do some parts of this story still contradict our best theories? These aren't just academic questions, they're clues to something much bigger. The reionization era holds the secrets to how everything we know, planets, life, even the atoms in our bodies came to exist. Yet for every answer we uncover, there are dozens of mysteries left hanging in the void. That's exactly what we're diving into today, 25 of the most captivating enigmas from this pivotal chapter in cosmic history. From ghostly signals hidden in the static of deep space to the elusive forces that sculpted the first galaxies, we're about to explore the frontiers of what science knows and what still keeps astronomers up at night. This isn't just a story about the past, it's a detective story, one where every clue brings us closer to understanding our place in the universe. So let's rewind the clock way back to a time when the cosmos was just learning how to shine. The very first spark that ended the Cosmic Dark Ages is still shrouded in mystery. What cosmic matchstick ignited the hydrogen fog that filled the early universe? Scientists are locked in a fierce debate, and the leading suspect sounds like something from science fiction. Population 3 stars. These weren't just any stars. They were titans, hundreds of times more massive than our sun, burning hot and fast with pure hydrogen and helium. When they exploded as supernova, their blistering ultraviolet radiation could have ripped electrons from surrounding hydrogen atoms, turning the murky cosmos transparent. But here's the catch, we've never actually seen one of these primordial giants. Every simulation says they should exist, yet the deeper we look into the early universe, the more their absence puzzles us. Then there's the black hole theory. Some astronomers argue supermassive black holes, feasting on gas in the cores of early galaxies, could have pumped out enough high-energy radiation to do the job. Recent observations of distant quasars, luminous beasts powered by these black holes, show they were already active surprisingly early. But if they were the main drivers of reionization, why do some patches of the universe appear to have cleared out faster than others? The data doesn't quite fit, and what if we're missing something entirely? A handful of researchers are chasing wilder ideas: cosmic strings, exotic particles, even collisions between early galaxies releasing bursts of energy we don't fully understand. The truth is, every time new telescopes like the James Webb Space Telescope peer deeper into the past, they throw fresh wrinkles into the story. Some regions of space seem to have reionized earlier than theories predict, while others stubbornly held onto their hydrogen fog longer than they should have. It's as if the universe flickered to life unevenly, like a string of Christmas lights with half the bulbs refusing to turn on. This isn't just academic curiosity. The trigger of reionization shaped everything that came after: how galaxies formed, where stars clustered, even the chemistry that made life possible. Solve this and we unlock the first real chapter in our cosmic origin story. But for now, the question lingers like an echo from the dawn of time: what or who turned on the lights? Those first galaxies were cosmic underdogs, small, dim, and staggeringly fragile compared to the giants we see today. Yet somehow, these fledgling collections of stars may have played an outsized role in ending the universe's dark ages. The problem, when astronomers tally up all the light these early galaxies should have produced, the numbers don't add up. There's a glaring gap, what scientists call the missing photons problem. If these galaxies were the primary engines of reionization, their combined ultraviolet glow falls shockingly short of the energy needed to strip electrons from all that cosmic hydrogen. It's like trying to heat an entire city with a handful of matchsticks. Enter the James Webb Space Telescope, our most powerful time machine yet. Peering deeper into the infrared than any instrument before it, Webb has begun spotting galaxies so faint and distant they were previously invisible. Some of these ghostly systems are pumping out far more ultraviolet radiation than their size suggests possible, hinting at frenetic star formation crammed into tiny volumes of space. Others appear to be shrouded in thick dust, their light dimmed but not extinguished like embers glowing beneath cosmic ash. Could there be whole populations of these hidden galaxies, their contributions to reionization overlooked until now? But even Webb's revelations come with twists. Some of these newly discovered galaxies seem too mature for their age, packed with metals and complex structures far earlier than models predicted. If galaxies grew up faster than we thought, did they also flood the universe with ionizing radiation sooner? And what about the smallest galaxies, those puny dwarfs barely massive enough to hold themselves together? Simulations suggest they should have been factories of ultraviolet light, but cosmic detectives struggle to find enough of them in the observational record. Perhaps the answer lies not in individual galaxies but in their collective behavior. Recent studies suggest the early universe might have been a galactic hive mind with countless small galaxies working in concert. Their combined radiation could have created overlapping bubbles of ionized gas, like a sponge gradually saturated with light. Or maybe the key was something more violent, epic collisions between young galaxies triggering bursts of star formation, each explosion ripping through the hydrogen fog like a chain reaction. One thing's certain, the more we learn, the less tidy the story becomes. Every new observation forces us to rewrite the rules of how galaxies grow and how they reshaped the cosmos. What started as a simple question, did early galaxies reionize the universe, has spiraled into a web of even deeper mysteries. And with Webb continuing to scan the skies, we're bound to find more surprises hiding in the faint glow of those first starlit islands. If the universe's reionization were a painting, it wouldn't be a smooth watercolor, it would be a splatter of scattered brushstrokes, uneven and chaotic. This patchwork cosmos is one of the most baffling revelations from modern astronomy. Instead of hydrogen gas clearing uniformly like fog burning off under morning sun, reionization happened in erratic bubbles. Some regions became transparent hundreds of millions of years before others, leaving vast pockets of stubborn darkness lingering like cosmic shadows. These bubbles weren't random. They clustered around sources of intense radiation, early galaxies or quasars, creating expanding spheres of ionized gas. But here's the twist. Simulations predicted these bubbles should grow in predictable, orderly ways. Instead, observations reveal a messy reality. Some bubbles grew enormous, spanning tens of millions of light years, while others stalled abruptly as if something or someone turned off the lights mid-process. The James Webb Space Telescope has spotted regions where reionization seems to have started and stopped multiple times, like a flickering light switch. What could cause such irregularity? One leading theory points to the cosmic web, the vast filamentary scaffolding of dark matter that underpins the universe. Denser nodes in this web might have hosted more galaxies, producing concentrated radiation that carved out bigger bubbles. Meanwhile, sparser regions lagged behind, trapped in darkness longer. But even this explanation falters when astronomers compare the distribution of these bubbles to the web's structure. Some voids in the cosmic web reionized surprisingly fast, while dense knots held onto their hydrogen fog stubbornly. Then there's the role of turbulence. Violent feedback from early supernova or black holes might have disrupted the smooth spread of ionization. Imagine blowing bubbles into a gusty wind. Some grow, some pop, others warp unpredictably. Similarly, bursts of star formation could have flooded their surroundings with radiation, only to collapse under their own weight, leaving half-finished ionization fronts frozen in time. This cosmic patchiness isn't just a curiosity, it's a clue. The unevenness hints at hidden players in reionization, perhaps undiscovered populations of dim galaxies, exotic physics in the early universe, or even the fingerprints of dark matter's mysterious behavior. Every irregularity in this ancient light map forces us to rethink how structure emerges in the cosmos. And with each new telescope probing deeper, the puzzle only grows richer, proving the universe's adolescence was far more turbulent than we ever imagined. Out in the cosmic wilderness, hydrogen atoms were the ultimate survivors, clinging to neutrality long after the blazing radiation of reionization should have wiped them out. Conventional wisdom said the universe's hydrogen fog had to vanish completely, ionized into oblivion by ultraviolet starlight, but the cosmos loves a good plot twist. The Lyman alpha forest, a strange pattern of absorption lines in quasar light, tells a different story. These spectral fingerprints reveal ghostly pockets of neutral hydrogen lingering like cosmic holdouts, defying expectations millions of years after reionization peak. How did these stubborn atoms escape annihilation? One clue lies in the densest regions of the early universe. Vast clouds of hydrogen, shielded by their own sheer mass, might have absorbed and scattered incoming radiation like a cosmic maze. Meanwhile, turbulent flows of gas churned by newborn galaxies could have created temporary shadows where ionization struggled to penetrate. Even today, simulations struggle to replicate these quirks. Some models suggest a few percent of neutral hydrogen survived, dispersed in filaments too faint for our telescopes to spot directly. Then there's the mystery of the Lyman alpha forest's limits. This cosmic barcode is our best window into hydrogen's fate, but it's frustratingly indirect. Quasar light passes through billions of light years of space, absorbing hints of neutral hydrogen along the way, but only if the gas is clumped just right. Diffuse hydrogen, spread thin across voids, slips through unnoticed. It's like trying to map a city's water system by only spotting the largest pipes. And what if some hydrogen didn't just hide, it fought back? Recent studies propose that collapsing gas in early galaxies might have cooled rapidly, recombining into neutral atoms faster than radiation could strip them apart. Picture a cosmic game of whack-a-mole, where ionized hydrogen keeps reverting to its neutral state in dense pockets. If true, reionization wasn't a one-way street, but a chaotic tug of war between light and matter. The implications ripple outward. Even a trace of leftover neutral hydrogen could have seeded later generations of stars or influenced the chemistry of evolving galaxies. Every unanswered question about these holdout atoms challenges our assumptions about how the universe transitioned from darkness to light, and whether the story is really as finished as we think. If you think setting a timeline for something as vast as the Cosmic Reionization Era would be straightforward, think again. The universe's adolescence is surprisingly hard to pin down, with even our most advanced instruments locked in a quiet but fierce debate. On one side, the Planck satellite's cosmic microwave background measurements suggest reionization was a late bloomer, wrapping up around 900 million years after the Big Bang. On the other, ancient quasars, those brilliant beacons powered by supermassive black holes, hint at a universe that cleared its hydrogen fog much earlier, with some regions ionizing before the 700 million year mark. That's a staggering 200 million year gap, a cosmic margin of error that leaves astronomers scratching their heads. The Planck data paints a broad brushstroke. By analyzing subtle distortions in the afterglow of the Big Bang, It captures the universe's average transition from neutral to ionized, but averages can be deceiving. Imagine trying to determine when autumn arrives by measuring the global temperature shift. Local variations get lost in the mix. Similarly, Planck's timeline might smooth over the universe's messy, uneven reionization, masking pockets where the process raced ahead or lagged behind. Quasars tell a different story. Their light, filtered through vast cosmic distances, carries absorption lines that act like time stamps. When astronomers study the most distant quasars, they occasionally hit a wall, a sudden drop-off in neutral hydrogen absorption, suggesting the gas around them had already been ionized. But here's where things get thorny. Some quasars show evidence of earlier reionization, while others, equally distant, seem to shine through lingering fog. It's as if the universe flicked on the lights in some rooms while leaving others dark, defying the idea of a single, clean timeline, the wild card galaxy formation. If the first stars and galaxies ignited earlier than we've accounted for, their radiation could have jump-started reionization in certain regions long before the broader cosmic average. Recent James Webb Telescope discoveries add fuel to this fire, spotting galaxies that look suspiciously mature for their age, their starlight potentially contributing to earlier ionization than models predicted. At the heart of this debate lies a deeper question. Was reionization a single, universal event or a patchwork of local transformations? The answer reshapes our understanding of how structure emerged in the cosmos, and whether the universe's grand narrative is smoother or far more chaotic than we ever imagined. Quasars should have been the ultimate cosmic floodlights in the reionization era, supercharged beacons powered by ravenous supermassive black holes, each capable of ionizing hydrogen across millions of light years. Yet when astronomers scour the early universe for these brilliant monsters, they come up nearly empty-handed. Where are they? The numbers don't add up. Simulations predict quasars should have been abundant enough to punch massive holes in the hydrogen fog, but observations reveal only a handful from this critical epoch. It's like searching for lighthouses in a storm and finding just one or two flickering weakly in the distance. One possibility is that these early quasars weren't absent, just hiding. Thick curtains of dust and gas might have shrouded their brilliance, muffling their light into near invisibility. Imagine a spotlight buried in a blizzard, the beams there, but you'd never know unless you stood right in front of it. The James Webb Space Telescope, with its infrared eyes, is uniquely equipped to pierce these cosmic veils. Already, it's spotting faint, reddened quasars that older telescopes missed, hinting at a hidden population lurking in the shadows. But dust might not be the only culprit. Perhaps quasars were genuinely rare in the reionization era, their formation stifled by the unique conditions of the young universe. Building a supermassive black hole requires a staggering amount of fuel, and the first galaxies might not have had enough dense gas to feed them efficiently. Some theories suggest these early black holes grew in fits and starts, starving for long periods before chaotic galaxy collisions dumped fresh material into their maws. If true, quasars would have flickered on and off like faulty street lamps, their sporadic bursts of radiation leaving patchy ionization trails. There's a wilder twist. What if the first quasars weren't where we're looking? Current surveys focus on the centers of galaxies, but in the chaotic early universe, supermassive black holes might have been ejected into the cosmic outskirts during violent mergers, their brilliant accretion disks glowing unseen in the void. Alternatively, some could have been smothered by their own outbursts, blowing away their gas supply in fiery winds before they reached full brightness. The stakes are high. If quasars played a bigger role in reionization than we've accounted for, their absence upends our models of how the universe cleared its hydrogen fog. Every missed quasar means a missing piece of the ionization puzzle, leaving gaps in the story of how light triumphed over darkness. With Webb peeling back the layers of cosmic dust and time, we might finally find these elusive giants, or confront an even deeper mystery about why the early universe kept its most powerful lights on dimmer switches. Dark matter might seem like an unlikely player in the story of cosmic reionization after all. It doesn't absorb, emit, or scatter light. But this invisible cosmic scaffolding could have been the unseen architect behind the entire process. Picture the early universe as a dimly lit construction site, with dark matter halos acting as hidden blueprints, guiding where galaxies and their ionizing radiation could form. The densest knots in this shadowy web became gravitational anchors, pulling in gas to fuel the first stars and black holes, while emptier regions remained dark and untouched. Without dark matter's invisible hand, reionization might have unfolded in a completely different way, or not at all. Simulations reveal just how crucial this connection could be. When researchers model the early universe with varying dark matter distributions, the differences are staggering. In scenarios where dark matter clumps more densely, galaxies form earlier and faster, flooding their surroundings with ultraviolet light like beacons in the void. But if dark matter is spread too evenly, galaxy formation stalls, leaving vast stretches of neutral hydrogen locked in darkness. Some models even suggest dark matter's microscopic properties, whether it's warm or cold. How it interacts with itself could have set the tempo for reionization's uneven progress. Yet for all these tantalizing clues, the dark matter link remains one of reionization's most speculative puzzles. Observations from the James Webb Space Telescope show galaxies forming in places dark matter models didn't predict, their brightness defying expectations. Other studies hint that dark matter halos might have been less efficient at gathering gas than simulations assumed, leaving gaps in the ionization map. And then there's the wild card. What if dark matter wasn't entirely passive? Theories like self-interacting dark matter propose these particles could collide, heat up, or even form their own shadowy structures, adding chaotic twists to reionization's timeline. The deeper we dig, the more questions arise. Did dark matter's subtle gravitational nudges create the perfect conditions for reionization? Or was its role more accidental, a cosmic stagehand rather than the director? Every new observation forces us to reconsider how much of this epoch's story is written in the invisible ink of the universe's most elusive substance. One thing's clear: solving reionization's mysteries might mean unraveling dark matter's secrets first. Imagine a cosmic prison break, countless ionizing photons, born in the hearts of early galaxies, desperately trying to escape and ionize the surrounding hydrogen fog. But most of them never made it out. This is the Lyman continuum escape problem, one of reionization's most perplexing roadblocks. Theory says these fledgling galaxies should have been spewing ultraviolet radiation like open fire hydrants, yet observations show only a trickle of ionizing photons actually leaked into intergalactic space. The rest trapped, absorbed, or diverted, as if some invisible warden locked the gates. Dust might be the prime suspect. In younger galaxies, thick clouds of cosmic soot could have absorbed escaping photons, turning their energy into heat before it ever reached the void. The James Webb Space Telescope has spotted galaxies from this era clogged with dust, their starlight dimmed and reddened like headlights in a sandstorm. But here's the puzzle: some of the dustiest galaxies still manage to leak a surprising number of ionizing photons, while seemingly pristine ones hold them back. It's as if the dust is arranged in cunning traps, not blanketing the galaxy evenly, but concentrated in labyrinthine pockets that let some light slip through cracks while smothering the rest. Then there's the role of galactic winds. Violent stellar explosions and black hole outbursts can blast gas and dust outward, carving temporary tunnels through a galaxy's atmosphere. These chimneys might offer photons a fleeting escape route, but they're chaotic and short-lived. Simulations show winds strong enough to punch holes in a galaxy's gaseous shroud, only for those gaps to snap shut moments later as gravity pulls the material back. The result, a flickering, unreliable release of ionizing radiation like a strobe light blinking through a thick fog. Hubble's observations added another layer of frustration. Scanning thousands of early galaxies, it found vanishingly few leaking the telltale Lyman continuum signal. Either our models vastly overestimate how many photons these galaxies produced, or something we're not even accounting for yet is intercepting them en masse. Could magnetic fields be corralling ionizing radiation? Are vast, unseen reservoirs of cold gas absorbing the photons before they cross into intergalactic space? The stakes couldn't be higher. If galaxies were the primary drivers of reionization, their inability to release enough ionizing photons leaves a glaring hole in the story. Every trapped photon is a missing piece of the puzzle, forcing us to reconsider whether we've underestimated the role of quasars, exotic particle decay, or even entirely unknown cosmic phenomena. Until we solve this escape problem, the true architects of the universe's grand illumination remain at large. Buried in the faint afterglow of the Big Bang, there's a whisper, a subtle distortion in the cosmic microwave background that might hold the key to reionization's deepest secrets. This ancient light, traveling for over 13 billion years, carries imprints of the universe's teenage years, etched into its polarization patterns like scratches on a time-worn record. Scientists call it the E-mode signal, a delicate swirl in the CMB's fabric caused by free electrons scattering photons during reionization. The stronger the signal, the more dramatic the ionization, at least in theory. But here's the catch: the signal we've detected is bafflingly weak, suggesting reionization was either slower, patchier, or stranger than our models predicted. Why is this signal so faint? One explanation points to timing. If reionization happened gradually over hundreds of millions of years, its mark on the CMB would be diluted, like a drop of ink stirred slowly into a vast ocean. Alternatively, if most ionization occurred in brief, violent bursts, quasar eruptions, or galaxy collisions, the signal might be concentrated in spikes too narrow for current telescopes to resolve. There's even a tantalizing possibility that dark matter played a role, its shadowy interactions subtly altering how free electrons scattered light, but the real frustration lies in the noise. The CMB's polarization patterns are drowned in a sea of galactic foregrounds, dust, synchrotron radiation, and other interference that muddies the waters. It's like trying to hear a single instrument in a symphony where the musicians keep shifting seats. Current telescopes like Planck and the South Pole Telescope have pushed the limits of detection, but their maps remain frustratingly blurred. That's where next-generation observatories come in. Projects like the Simons Observatory and CMB-S4, armed with thousands of ultra-sensitive detectors, aim to filter out the cosmic static and isolate reionization's fingerprint with unprecedented clarity. These instruments won't just sharpen the signal, they'll trace its variations across the sky, revealing whether reionization unfolded in synchronized waves or a chaotic starburst of isolated events. Some might even spot the elusive B-mode polarization, a curl pattern that could hint at inflation-era gravitational waves intertwined with reionization's aftermath. The stakes couldn't be higher. If these faint CMB whispers finally speak clearly, they could settle century-old debates. Did galaxies or quasars dominate reionization? How much did dark matter contribute? And was this cosmic transition as orderly as textbooks suggest, or a messy, fractured revolution? For now, the answers remain encrypted in those primordial photons, waiting for the right telescope to crack their code. Just as the first stars were flooding the universe with ultraviolet light, another cosmic power was awakening supermassive black holes, devouring gas at the hearts of young galaxies and unleashing torrents of radiation. These active galactic nuclei, or AN, burned with terrifying brilliance, their energy output dwarfing entire galaxies. And here lies a tantalizing puzzle. Did these monsters accelerate reionization, or were they merely spectators to a process already dominated by starlight? The answer could rewrite our understanding of how the universe transformed from darkness to light. Take the case of quasars, the brightest AGNs. Their piercing beams of X-rays and ultraviolet radiation could ionize hydrogen far beyond their host galaxies, carving vast bubbles in the cosmic fog. Some theorists argue they were the heavy artillery of reionization, punching through dense regions of gas that starlight alone couldn't clear. Yet for all their power, quasars were rare. Even the most optimistic estimates suggest they were outnumbered by galaxies 1,000 to 1. Could a handful of these brilliant beacons really have outshone the collective glow of countless stars? The numbers tell a conflicting story. When astronomers calculate the total ionizing radiation from known quasars in the reionization era, it falls short by a lot. Even factoring in obscured AGNs lurking behind dust clouds, the energy deficit remains. But simulations reveal a loophole. If early supermassive black holes were more efficient than we thought, their radiation might have traveled farther, ionizing hydrogen at distances starlight couldn't reach. Some models suggest AGN photons, with their higher energies, could escape galaxies more easily, slipping through the same dust barriers that trapped stellar ultraviolet. Then there's the timing problem. The oldest quasars we've spotted ignite well into reionization's peak, raising the question, were they latecomers to the party? Recent James Webb Telescope data complicates the picture, with hints of earlier black hole activity nestled in unexpectedly mature galaxies. If AGNs flickered on sooner than we've detected, their cumulative effect might have been profound. Alternatively, their intermittent outbursts could explain why reionization progressed unevenly brief, violent surges of ionization followed by long lulls. Meanwhile, the star-dominated model faces its own contradictions. While galaxies undoubtedly pumped out vast UV radiation, their light was often trapped by local gas, leaving large swaths of the intergalactic medium untouched. AGNs could have been the cosmic cleanup crew, ionizing the stubborn pockets that stars couldn't crack. Or perhaps the truth lies in an unexpected synergy, black holes and stars working in tandem, their combined radiation weaving the universe's luminous web. The stakes are high. If AGNs played a major role, our entire narrative of galaxy formation shifts. Black hole growth would no longer be a side effect of cosmic evolution, but a driving force. Yet with every new observation, the mystery deepens, leaving us to wonder, did reionization have one architect, or was it a collaboration between two cosmic titans? Population 3 stars were the titans of the cosmic dawn, colossal, fleeting, and made of nothing but hydrogen and helium, the pristine elements forged in the Big Bang's aftermath. These mythical beasts should have been the universe's first streetlights, their searing ultraviolet radiation tearing through the primordial hydrogen fog. Yet for all their theoretical importance, not a single one has ever been spotted. It's like searching for the bones of giants and finding only silence. So where did they go? The answer might lie in their own brilliance and their tragic fragility. Born in the densest pockets of the early cosmos, population 3 stars were unlike anything that exists today. With no heavier elements to cool their cores, they grew to staggering sizes, some reaching hundreds of solar masses. Their surface temperatures would have been blistering, emitting ultraviolet photons with enough energy to strip electrons from hydrogen atoms in a single strike. Simulations suggest just one of these stars could have ionized gas thousands of light years around it, a single match igniting a cosmic bonfire, but their ferocity came at a cost. Burning fuel at a breakneck pace, they lived fast and died young, exploding as supernova within a few million years. Their deaths were so violent, they might have scattered their ashes far into the void, leaving no trace behind. The hunt for these ghosts has turned up empty for decades. Telescopes like Hubble and now James Webb scan the deepest reaches of time, hoping to catch a glimpse of their telltale light. But population 3 stars pose a cruel irony. The very qualities that made them so important also made them nearly invisible. Without metals, their spectra lacked the distinctive fingerprints that astronomers rely on to identify stars. Their brief lifespans mean they blinked out before most telescopes could spot them. Even their supernova, though spectacular, might have been rare enough to evade detection. Some researchers argue we're looking in the wrong places. Instead of searching for intact stars, they suggest hunting for their chemical aftermath. When these behemoths exploded, they should have seeded their surroundings with the first heavy elements: carbon, oxygen, silicon, creating a faint but detectable pollution in later generations of stars. Yet even this cosmic forensics work has yielded mixed results. Some ancient stars show traces of primordial material, but none conclusively link back to population 3. Others propose these giants might have collapsed directly into black holes, vanishing without the fireworks of a supernova. The implications stretch far beyond stellar archaeology. If population 3 stars were rarer or shorter-lived than models predict, the entire timeline of reionization could unravel. Did other sources, dim galaxies, quasars, or even exotic particles, pick up the slack? Or does their absence hint at gaps in our understanding of how the first structures formed? Until we find proof of these elusive giants, their role in lighting up the cosmos remains one of reionization's most haunting gaps. Just when cosmologists thought they had reionization figured out, helium threw a wrench into the works. Hydrogen may have been the main event, but its heavier cousin added a bizarre second act to the cosmic light show, one that reshuffled the deck of our understanding. Unlike hydrogen, which reionized early under the harsh glare of massive stars, helium held onto its electrons much longer, only surrendering them when blasted by a far more extreme energy source. This two-stage cosmic awakening paints a messier picture than anyone expected, forcing us to rethink how and when the universe truly cleared its fog. The key difference lies in the numbers. It takes a staggering 24 electron volts to strip the first electron from helium, nearly double the energy needed to ionize hydrogen. Early starlight, fierce as it was, couldn't muster that kind of punch. Only the blistering X-rays from quasars and active galactic nuclei pack enough power to break helium's grip. Evidence for this lurks in the spectra of distant quasars, where sharp absorption lines betray vast reservoirs of helium that remained stubbornly neutral long after hydrogen had bowed to ionization. Then suddenly, around 2 to 3 billion years after the Big Bang, these lines vanish. Something or someone flipped the switch, but here's where the plot thickens. This delayed helium reionization didn't happen uniformly. Some regions of space appear to have cleared earlier, while others lagged, creating a patchwork similar to hydrogen's earlier struggles. The culprit's quasar variability. Unlike steady starlight, quasars flicker like cosmic strobes, their activity tied to the erratic feeding habits of supermassive black holes. A quasar's outburst could ionize helium in a vast bubble around it, but once it dimmed, distant gas might remain untouched. The result was a chaotic stop-start process that left the universe's helium partially transparent for billions of years. This double reionization scenario raises thorny questions. If quasars dominated helium's ionization, why didn't their X-rays also reionize hydrogen? The answer might lie in the cold, hard math of cross-sections, a photon's likelihood of interacting with an atom. X-rays sail through hydrogen like bullets through fog, rarely depositing enough energy to ionize it. Helium, with its tighter electron binding, acts like a net, catching these high-energy photons where hydrogen let them pass. It's a cosmic game of selective absorption where different elements respond to different triggers. Yet mysteries linger. The timing of helium reionization overlaps with the peak of quasar activity, but the correlation isn't perfect. Some quasars seem too dim, their numbers too sparse to account for the scale of ionization we observe. Could there have been a hidden population of faint AGNs, their collective X-rays doing the heavy lifting? Or might other exotic phenomena, decaying dark matter particles, perhaps have chipped in? The James Webb Space Telescope's deep infrared gaze may soon spot these missing actors, but for now, the helium puzzle remains a gap in the story of how the cosmos became transparent not once but twice. Worse still, this two-phase process muddles our cosmic chronometers. When we date reionization using hydrogen signatures, we're only seeing half the picture. Helium's later transition means the universe wasn't fully ionized as early as we thought, a realization that forces us to recalibrate everything from galaxy formation models to estimates of the intergalactic medium's temperature. It's a humbling reminder that the cosmos rarely follows a single, tidy narrative. Instead, it layers complexity upon complexity, daring us to keep up with its twists. Deep in the static of the universe's oldest radio waves, there's a whisper, a faint, ghostly signal that could rewrite the story of reionization. It's called the 21-centimeter line, the signature of neutral hydrogen atoms quietly humming across the cosmos. When the first stars flickered to life, their ultraviolet radiation should have left a scar in this signal, a dip where hydrogen absorbed and re-emitted light at this precise wavelength. For decades, astronomers have chased this cosmic fingerprint, hoping it would reveal exactly when and how the universe woke up. Then, in 2018, the EDGES experiment dropped a bombshell. They detected a dip, all right, but it was far deeper than anyone predicted, plunging like a cosmic canyon where scientists expected only a shallow ripple. The EDGES team's announcement sent shockwaves through astrophysics. Their data suggested neutral hydrogen in the early universe was colder than models allowed, or the background radiation bathing it was hotter. Either scenario would upend our understanding of cosmic dawn. One radical explanation: dark matter interactions. If unseen particles collided with hydrogen, sapping its thermal energy, that could explain the frigid temperatures needed for such a dramatic dip. Another idea posits that the first stars or black holes flooded space with extra radio waves, artificially amplifying the background against which the 21-centimeter line appears. Both theories are unsettling. Dark matter wasn't supposed to interact this way, and early galaxies shouldn't have produced that much radio noise, but skepticism runs deep. Critics argue the signal might be earthly interference masquerading as cosmology, perhaps a glitch from the instrument itself or a ripple from our own atmosphere. EDGE's setup was ingenious yet humble, a table-sized antenna in the Australian outback designed to filter out modern radio chatter and listen for primordial whispers. Yet isolating a 17 MHz whisper buried under 13 billion years of cosmic noise is like trying to hear a pin drop in a hurricane. Follow-up experiments like Sarah's and Leda have failed to confirm the dip, leaving the field in limbo. The stakes are dizzyingly high. If EDGE's signal is real, it implies reionization began earlier and more violently than we thought, with galaxies or exotic physics heating hydrogen far ahead of schedule. If it's noise, we're back to square one in the hunt for this elusive radio echo. Next-generation projects like the Square Kilometre Array aim to settle the debate, mapping the 21-centimeter signal across the sky with unprecedented precision. They'll scan for not just the dip's depth but its structure, whether it's smooth or patchy, hinting at the uneven spread of the first stars. For now, the 21-centimeter signal remains a tantalizing maybe, a shadow flickering at the edge of detection. Whether it's a breakthrough or a mirage, one thing's certain: the universe's oldest radio station is still playing, and we're just learning how to tune in. Somewhere in the void between the Big Bang's fading afterglow and the first starlight, the universe hit snooze. Theory says stars should have ignited by 200 million years after creation. Yet observations suggest they flickered on tens of millions of years later, a cosmic tardiness that defies our best simulations. What stalled the dawn? The answer might lie in the fragile dance between dark matter and the first delicate clouds of gas, a partnership that took longer to kindle than anyone anticipated. Take primordial gas clouds, the nurseries of the first stars. These patches of hydrogen and helium needed to cool dramatically before gravity could crush them into stellar sparks. Normally, molecules like hydrogen deuteride or even plain hydrogen atoms help shed heat by radiating energy away. But in the pristine early universe, missing heavier elements meant fewer cooling pathways. Gas might have swirled anxiously in place, too warm to collapse, like steam struggling to condense without a cold surface. Some models suggest this thermal gridlock could have delayed star formation by 15%, buying the universe extra time in darkness. Then there's dark matter's subtle sabotage. Most simulations assume it acted as a passive scaffold, its gravity herding gas into dense clumps. But what if it wasn't so hands-off? Hypothetical, interacting dark matter could have bumped into gas particles, transferring minuscule amounts of kinetic energy, just enough to keep the gas slightly warmer for longer. Alternatively, if dark matter was fuzzy or warm, with lighter, faster-moving particles, its gravity might have been too weak to quickly pull gas into star-forming knots. The result, a sluggish start to cosmic dawn, with galaxies assembling in slow motion. Observations add fuel to the mystery. The James Webb Space Telescope has spotted galaxies from this epoch that look suspiciously mature for their age, their advanced structures hinting at earlier star formation than the overall cosmic timeline suggests. This paradox, delayed ignition but unexpectedly evolved galaxies, implies the universe didn't wake up uniformly. Some regions might have raced ahead while others languished, trapped in a thermal standoff between gas physics and dark matter's invisible rules. The implications ripple far beyond stellar punctuality. If cooling inefficiencies or dark matter's quirks delayed reionization, they also reshaped the types of stars that dominated the early universe. Colder gas tends to fracture into smaller fragments, birthing more numerous but dimmer stars. Warmer delays might have allowed rarer, monstrous population 3 stars to form, their explosive death scattering heavy elements sooner. Every million years of delay recalibrates our understanding of how quickly or chaotically the cosmos learned to shine. Perhaps the real lesson is that the universe wasn't in a hurry. The same forces that kept it dark longer might have set the stage for a richer, more intricate age of light, one where stars didn't just flicker on, but emerged precisely when the cosmos was ready for them. Early supernovae should have been the ultimate cosmic recyclers, exploding in spectacular fashion to forge heavy elements and trigger new waves of star birth. But what if these violent deaths actually smothered the very process they were supposed to fuel? This is the feedback conundrum, a paradox where the same explosions that lit up the early universe may have also slammed the brakes on reionization progress. Picture a fledgling galaxy, its first generation of massive stars reaching the end of their brief lives. When these giants detonate as supernova, they blast their surroundings with shockwaves and metal-rich debris ingredients that should theoretically seed the next round of star formation. Yet simulations tell a different story. In the pristine environments of the early universe, these blasts were so powerful they didn't just enrich nearby gas clouds, they vaporized them. The resulting bubbles of hot, turbulent gas could take hundreds of millions of years to cool enough for gravity to pull them back into stellar nurseries. Instead of jump-starting star formation, these supernovae might have left behind cosmic dead zones, regions so disrupted they temporarily starved galaxies of fresh star fuel. But the plot thickens. Not all feedback is negative. Some models suggest a delicate balance. While supernova cleared space around them, their shockwaves also compressed distant gas pockets, triggering secondary star formation far from the explosion's epicenter. Imagine tossing a stone into a pond. The initial splash devastates the water's surface, but the ripples can nudge floating leaves into new patterns. Similarly, certain galaxies might have harnessed this positive feedback, channeling supernova energy to ignite stars in synchronized waves. The James Webb Space Telescope has spotted galaxies from this epoch with oddly clustered star formation, their stellar populations grouped like pearls on a string, a possible fingerprint of this push and pull dynamic. The stakes: timing. If negative feedback dominated, reionization would have progressed in fits and starts, with galaxies flickering as they cycled through bursts of star formation and disruptive explosions. Positive feedback, on the other hand, could have sustained a steadier glow, allowing ionizing radiation to build momentum. The challenge is untangling which process won out. Metal-poor stars in ancient galaxies offer clues. Their compositions hint at how efficiently supernova debris was recycled. Too few metals might mean most material was blown away entirely. Just the right amount could signal a Goldilocks scenario where feedback balanced creation and destruction. Yet even these stellar fossils can't settle the debate. Some regions of the early universe reionized smoothly, while others stuttered. Perhaps the answer isn't either or but a cosmic seesaw, with feedback's role shifting based on local conditions. Dense environments might have muted supernova's destructive power, their thick gas absorbing shockwaves like a cosmic sponge. In sparser regions, explosions could have run rampant, leaving behind voids where reionization lagged. One thing's clear: the universe's first explosions weren't just fireworks, they were architects shaping the destiny of light itself. Now a wild card: what if supernova weren't the only players? Black hole jets and stellar winds from massive stars could have contributed their own feedback loops, stirring the cosmic pot in ways we're only beginning to model. As telescopes probe deeper into the reionization era, each new galaxy reveals another piece of this intricate puzzle, one where destruction and creation danced on a knife's edge. Dust wasn't supposed to be a factor in the reionization era, at least not this early. Conventional wisdom held that the first galaxies were pristine, their gas untouched by the heavier elements needed to form soot-like grains. Yet mounting evidence suggests cosmic dust was already lurking in these infant star systems, cloaking their light and throwing a wrench into our calculations of how much ionizing radiation they actually released. This isn't just a minor detail, it's a potential game changer. If dust formed faster than anyone predicted, we might have seriously underestimated how many photons were trapped before they could escape and clear the cosmic fog. Take the case of MAX 1149 GD1, a galaxy spotted by the James Webb Space Telescope shining from just 500 million years after the Big Bang. Its light carries the unmistakable signature of dust, a faint reddening that betrays the presence of tiny solid particles absorbing shorter wavelengths. For dust to exist this early, stars must have lived, died, and forged heavy elements in a blink of cosmic time. But here's the catch: every photon absorbed by dust is a photon that never reached intergalactic hydrogen. If even a fraction of early galaxies hid behind these sooty veils, their contribution to reionization could have been wildly miscalculated. The implications spiral outward. Dust doesn't just dim light, it scatters and re-emits it at longer, less energetic wavelengths. Ultraviolet photons capable of ionizing hydrogen might get converted into harmless infrared, like a firefly trapped in smoke. Some simulations suggest dust could have reduced escaping ionizing radiation by half in certain galaxies, enough to flip the script on whether these systems were major players in reionization or mere bystanders. But confirmation is tricky. Dust's effects vary wildly depending on its composition, temperature, and distribution. Clumped near star-forming regions, it could act like a photon prison. Spread diffusely, it might merely tint a galaxy's glow without stifling its ionizing power. Then there's the bigger question: how did dust form so fast? One theory points to supernova. The deaths of massive stars in the first 100 million years could have spewed carbon and silicon into space, where they condensed into microscopic grains. Another idea involves asymptotic giant branch stars, cooling giants that belch out dust in their final throes. but both scenarios stretch our understanding of stellar evolution timelines. Alternatively, some researchers propose that dust might have formed directly in frigid molecular clouds, skipping the need for multiple stellar generations entirely. The wild card here is observational bias. Our telescopes naturally spot the brightest, most extreme galaxies first. If dust preferentially obscured smaller, dimmer systems, we might be missing entire populations that actually drove reionization. Imagine judging Earth's weather by only sampling deserts. You'd miss the rain entirely. Similarly, the galaxies we've catalogued could be the exceptions rather than the rule, their dust content skewing our perception of the epoch's true dynamics. Unraveling this mystery will take more than sharper telescopes. It requires peeling back layers of cosmic chemistry, stellar physics, and even the conditions inside those first supernovae. Every speck of dust holds a story, one that might rewrite how we reckon the universe's great awakening. And with Webb now probing deeper into infrared wavelengths, we're finally getting a clear look at what's been hiding in the shadows all along. Reconstructing the Cosmic Reionization Era is like trying to balance an ancient ledger, except the numbers refuse to add up. When astronomers tally all the ionizing photons produced by known sources, early galaxies, quasars, even those hypothetical population 3 stars, the total falls shockingly short. We're missing at least half the energy needed to strip every hydrogen atom in the universe of its electron. It's the ultimate cosmic accounting error, forcing scientists to ask, were there secret photon factories hiding in the early cosmos, or do we fundamentally misunderstand how light escaped its origins? Start with galaxies, the presumed workhorses of reionization. Even after accounting for all the ultraviolet radiation they produced, models show most of those photons never made it past their home galaxy's gas clouds. Dust absorbed some, others were scattered or reabsorbed locally. The result, a paltry escape fraction, with only 5 to 20% of ionizing photons breaking free to do the real work of clearing the cosmic fog. Multiply that by the number of galaxies we've observed, and the deficit becomes glaring. Either early galaxies were far more efficient photon producers than we've detected, or something else was quietly pumping radiation into the void. Quasars can't close the gap. While their brilliant beams of X-rays and ultraviolet light pack a powerful punch, they were simply too rare in the reionization era. Even if every known early quasar worked overtime, their combined output would barely nudge the cosmic ledger toward balance. Some theorists suggest we're missing a hidden population of mini-quasars, smaller, dimmer active galactic nuclei obscured by dust or tucked away in dwarf galaxies. The James Webb Space Telescope might soon spot these elusive objects, but for now they remain ghosts in the equations. Then there's the wild card, decaying dark matter. A handful of physicists speculate that certain exotic particles could have released ionizing radiation as they decayed in the early universe. This shadowy process would have been diffuse but omnipresent, like a faint glow permeating all of space. The idea remains controversial, but it underscores the desperation of the photon budget crisis when conventional sources come up short. Even the fringes of physics get a seat at the table. Perhaps the answer lies in the overlooked extremes. Recent observations reveal that the smallest, faintest galaxies, those barely visible even to Webb, might have been photon powerhouses relative to their size. Their shallow gravity wells could have let ionizing radiation escape more easily, while their sheer numbers added up to a significant cumulative effect. Alternatively, brief but violent events, galaxy collisions, black hole mergers, or hypernova, might have unleashed concentrated bursts of ultraviolet light that conventional surveys miss. The deeper we dig, the clearer it becomes. Reionization's energy budget isn't just a math problem. It's a window into the gaps in our cosmic census, hinting at forces and phenomena we've yet to uncover. Every missing photon represents a hidden chapter in the universe's story, one we're only beginning to decode. the faintest galaxies in our cosmic backyard might be hiding the oldest secrets of reionization. Dwarf galaxies in the local group, those tiny, dim companions to the Milky Way and Andromeda, behave like cosmic fossils, their star formation histories frozen in time. While most galaxies evolved dramatically over billions of years, these relics seem to have pressed pause during the epoch when the universe first lit up. Their ancient stars, pristine gas clouds, and oddly stunted growth could be the missing keys to understanding how reionization unfolded in real time. Take Leo T, a dwarf galaxy so faint it was only discovered in 2006. Unlike younger galaxies buzzing with newborn stars, Leo T's star formation sputtered out early, leaving behind a population of elderly stars and a surprising amount of neutral hydrogen, the same raw material that filled the universe before reionization. It's as if this galaxy got stranded in the past, preserving conditions eerily similar to the cosmic dawn. By studying its gas content and stellar chemistry, astronomers can reverse engineer how ultraviolet radiation from the first stars might have interacted with such environments. The clues are subtle but telling. An overabundance of old, metal-poor stars suggests star formation was abruptly quenched, possibly when reionization's harsh radiation heated the galaxy's gas, preventing it from cooling and collapsing into new stars. Then there's Segue 1, an ultra-faint dwarf so wispy it barely qualifies as a galaxy. Nearly all its stars formed over 12 billion years ago, then nothing. Its stunted evolution implies something catastrophic happened early on, and reionization is the prime suspect. Unlike larger galaxies, which could shield their gas with gravity and dust, tiny dwarfs like Segue 1 were sitting ducks. The moment the cosmic UV flood hit, their shallow gravitational wells couldn't hold onto their gas, leaving them starved and sterile. These galaxies aren't just bystanders, they're casualties of the very process we're trying to decode. But the plot thickens when you compare them to slightly more massive dwarfs like Carina or Fornax. These galaxies show multiple bursts of star formation, with gaps of billions of years between them. That stuttering rhythm hints at a tug-of-war: initial star birth, then reionization's heat shutting things down, followed by a delayed resurgence as gas slowly cooled and fell back in. It's a pattern that mirrors the stop-start nature of reionization itself, where some regions ionized early while others held out. The local group's dwarfs aren't a monolith, they're a mosaic of survival strategies, each encoding different chapters of the epoch's story. The real jackpot lies in their chemical fingerprints. Stars born before reionization contain almost no heavy elements, forged exclusively in the depths of those first massive stars. Find enough of these pristine stars in nearby dwarfs, and you've effectively built a time machine. Already, the Milky Way's own halo has yielded stars with iron abundances 100,000 times lower than the Sun's, likely refugees from ancient dwarf galaxies torn apart long ago. Their compositions suggest they formed in environments where supernovae were rare, implying their host systems were small and fragile, easily disrupted by reionization's pressures. Yet even these galactic fossils come with puzzles. Some ultra-faint dwarfs, like Tucana 2, host stars with bizarrely high levels of R-process elements, heavy metals typically forged in neutron star collisions. How did such delicate galaxies retain enough gas to form stars after these violent events? Did reionization's heat pulse trigger secondary star formation in ways we don't yet understand? Or are we seeing the ghosts of galaxies that somehow weathered the storm? The answers won't come easy. These dwarfs are dim, their stars sparse, and their signals buried in noise. But next-generation telescopes like the Vera Rubin Observatory aim to discover hundreds more, building a statistical map of survival and ruin. Each new fossil galaxy adds another piece to the puzzle, not just of how the universe woke up, but of why some galaxies thrived while others became cosmic relics frozen in time. The cosmic web wasn't just a backdrop for reionization, it might have been the master architect. This sprawling network of dark matter and gas filaments, invisible to the naked eye, wove the universe into a labyrinth of highways and dead ends. And where those filaments crossed, they funneled ionizing radiation like fiber optic cables, carving paths through the hydrogen fog with eerie precision. But how much of reionization's uneven progress was dictated by this hidden scaffolding? Simulations are now revealing a tantalizing answer. The cosmic web didn't just shape where galaxies formed, it controlled how their light reshaped the cosmos. Picture the early universe as a vast, tangled river system. The densest knots of the cosmic web, where multiple filaments converged, acted like bustling ports, gathering gas to birth galaxies and quasars. From these hubs, ultraviolet radiation could race down the filaments, traveling far beyond its source. Recent supercomputer models show these structures behaving like ionization superhighways, with photons streaming along filaments at speeds that defied the era's average expansion. A single quasar at a major intersection might light up entire filamentary branches, while galaxies strung along these cosmic threads became relay stations, amplifying the signal as it passed. Yet the web's role wasn't purely facilitative. Its topology also created cosmic roadblocks. Vast voids between filaments acted like deserts where radiation struggled to penetrate. Without dense gas to absorb and re-emit photons, these regions remained dark long after their filamentary neighbors had cleared. Meanwhile, tightly wound knots in the web could trap radiation, creating feedback loops where ionized gas cooled and recombined faster than new photons arrived. The result, a patchwork of ionization so intricate it resembles less a spreading wildfire and more a circuit board lighting up in disconnected sectors. Observational evidence is mounting to support this. The Lyman alpha forest absorption lines in quasar spectra reveals where neutral hydrogen clung to the cosmic web's filaments long after surrounding voids had ionized. And the universe's largest structures today, like the Sloan Great Wall, still trace the ghostly outlines of these ancient ionization pathways, but the simulations aren't perfect. Some predict filaments should have glowed faintly as they conducted radiation, a signal no telescope has yet detected. Others struggle to explain why certain filaments reionized earlier than their density alone would suggest. The wild card, turbulence. Early galaxies and quasars didn't just sit quietly at the web's nodes, they erupted with supernova and black hole jets stirring the gas around them. This chaos might have warped nearby filaments into temporary curves or kinks, creating shortcuts or detours for traveling radiation. Imagine a highway system where construction crews randomly add overpasses overnight. The James Webb Space Telescope's deep field images are now catching hints of this, showing galaxy alignments along filaments that don't match pristine simulations. Some filaments appear ionized far beyond where models say galaxy light should reach, as if unknown forces were at work. If the cosmic web really was reionization's silent conductor, it reshuffles our understanding of cosmic dawn. Galaxies and quasars weren't just isolated light sources, they were nodes in a vast, luminous network, their influence magnified or muffled by the universe's hidden architecture. And perhaps that's the most profound lesson. The cosmos didn't wake up randomly. It followed a blueprint we're only now beginning to trace, written in the language of dark matter and ionized gas. X-rays, the invisible, high-energy fingerprints of the universe's most violent events, might have played a sneaky role in reionization, but whether they helped or hurt the process is a cosmic tug-of-war. Deep in the early cosmos, binary star systems packed with neutron stars or black holes were likely spewing X-rays as they devoured gas from their companions. These relentless rays didn't just pierce the darkness, they could have subtly preheated the hydrogen fog, warming it just enough to make it easier for ultraviolet light to finish the ionization job. Think of it like thawing ice before breaking it. X-rays may have softened the cosmic gas, reducing the energy needed to strip electrons away, but there's a twist. That same preheating might have backfired. Warmer gas can cool more efficiently by radiating energy away, clumping together faster and shielding itself from further ionization. In this scenario, X-rays wouldn't be allies, they'd be saboteurs, helping hydrogen regroup into dense clouds that starlight couldn't penetrate. Simulations paint a chaotic picture. In some regions, X-rays smooth the path for reionization. In others, they slam the brakes by accelerating gas collapse. The difference could come down to timing. Early, gentle X-ray heating might have primed the universe for ionization, while a later, more intense bombardment could have overstimulated cooling, leaving pockets of stubborn neutrality. The smoking gun, faint, distant galaxies emitting X-rays without the fireworks of quasars. The James Webb Space Telescope has spotted hints of these systems, their radiation signatures suggesting they were more common in the early universe than previously thought. Yet even with these observations, the puzzle persists. Some models show X-rays creating bubbles of warm gas around early binaries, ideal conditions for later ultraviolet light to ionize. Others suggest the same X-rays triggered a cascade of hydrogen molecule formation, a cooling effect that could have starved galaxies of the raw material needed to keep producing ionizing stars. The answer might lie in the Goldilocks zone, just enough X-rays to warm the gas, but not so much that it fragments prematurely. It's a delicate balance, one that could explain why reionization unfolded unevenly across the cosmos. Too much X-ray activity in one region might have stifled progress, while a quieter corner of the universe with gentler preheating could have cleared its hydrogen fog with ease. The deeper we look, the clearer it becomes. X-rays weren't just background noise in cosmic dawn. They were wildcards capable of either lighting the fuse or snuffing it out. If galaxies were the engines of reionization, what sparked them to life in the first place? This cosmic chicken or egg dilemma cuts to the heart of the era's greatest paradox. Did the first stars and galaxies carve out ionized bubbles that then nurtured more galaxy formation? Or did galaxies emerge first, their radiation creating the bubbles as a side effect? The answer isn't just academic, it reshapes our entire understanding of how structure emerged in the early universe. One school of thought suggests ionization bubbles came first. In this scenario, dark matter's gravitational pull gathered hydrogen into dense knots, but without stars to heat the gas, these proto-galactic clouds remained too warm to collapse. Then, somewhere in the void, a random fluctuation, perhaps a slightly denser patch of dark matter, triggered the first star. Its radiation ionized a small bubble around it, cooling the gas within by stripping away electrons. This cooler gas could then collapse more easily, birthing second-generation stars and tiny galaxies. Like a chain reaction, these new galaxies expanded their bubbles, creating a network of ionized zones where further galaxy formation thrived. The bubbles, in essence, became cosmic nurseries, but there's a competing vision. Some simulations show galaxies forming independently, their starlight carving out ionized bubbles only after they'd already taken shape. In this version, the first galaxies were born in neutral hydrogen, their stars fighting against the surrounding fog. Only once enough galaxies clustered together did their combined radiation overwhelm the hydrogen, punching through like sunlight breaking a morning mist. The difference here is critical. If galaxies formed first, reionization was a top-down process driven by large-scale structure. If bubbles led the way, it was bottom-up, a grassroots revolution where small pockets of change snowballed into a cosmic transformation. Observational clues are maddeningly ambiguous. The James Webb Space Telescope has spotted galaxies in the early universe that appear suspiciously mature, their advanced structures suggesting they formed in pre-ionized environments. Yet other regions show galaxies embedded in stubbornly neutral gas, their light struggling to escape. It's as if both scenarios played out simultaneously, with different corners of the universe following different rulebooks. The wildcard feedback loops. Early supernova could have blown gas out of galaxies, starving them of star-forming material and stunting their growth. In bubbled regions, this gas might have been recaptured by neighboring galaxies, fueling further ionization. Meanwhile, in neutral zones, ejected gas might have drifted away forever, leaving galaxies stranded in isolation. The cosmic web adds another layer. Filaments of dark matter could have funneled gas into ionized zones, creating a self-reinforcing cycle where bubbles attracted more gas, which birthed more galaxies, which expanded the bubbles further. The stakes are dizzying. If bubbles came first, then dark matter's subtle whispers dictated the universe's reawakening. If galaxies led the charge, their starlight was the true architect. Perhaps the answer lies somewhere in between, a chaotic dance where both forces shaped each other in turn, their partnership scribbled across the cosmos in light and shadow. Until we peer even deeper into the past, this cosmic, which came first, will keep astronomers arguing and the universe chuckling at our attempts to pin it down. Satellite galaxies orbiting larger ones like the Milky Way should be cosmic time capsules, relics from the reionization era frozen in their infancy. Yet when astronomers count them, the numbers don't add up. There are far fewer than simulations predict. This isn't just a head-scratcher for galaxy formation. It throws a wrench into reionization's entire narrative. If these faint dwarfs were as scarce back then as they appear now, how did the universe muster enough ionizing radiation to clear the hydrogen fog? The answer might rewrite our understanding of dark matter's role in lighting up the cosmos. Take the classic missing satellites problem. Supercomputer models of cosmic structure formation, based on our best dark matter theories, predict thousands of small satellite galaxies swarming around each Milky Way-sized system. But telescopes spot only a few dozen. Some blame observational limits. These dwarfs are dim, often cloaked in dust or spread so thin they blend into the background. Others argue they existed but were obliterated by reionization's harsh ultraviolet glare, their gas stripped away before they could form many stars. The survivors, like the Milky Way's ultra-faint companions, might be the lucky exceptions, galaxies just dense enough to cling to their gas against the cosmic UV onslaught. But here's where it gets thorny for reionization. If most satellite galaxies were sterilized early, they couldn't have contributed much ionizing radiation. Yet models relying on larger galaxies alone struggle to produce enough UV light to match the pace of reionization we observe. This forces an uncomfortable question. Were there hidden legions of tiny, ultra-faint dwarfs back then that have since vanished? The James Webb Space Telescope offers tantalizing hints, spotting distant galaxies so diffuse they'd be invisible to older instruments. If these fragile systems were more abundant in the early universe, they might have punched above their weight, their collective starlight ionizing vast volumes before fading into obscurity. Dark matter's quirks could hold the key. Most simulations assume it's cold, slow-moving and clumpy. But what if it's warm, with lighter, faster particles? Warm dark matter would suppress the formation of tiny halos, neatly explaining the satellite shortage. Yet tweaking dark matter's properties creates new headaches. Too warm, and galaxies form too late to drive reionization. It's a cosmic tightrope walk where adjusting one variable sends others tumbling. Perhaps the answer lies in demolition rather than disappearance. Early satellite galaxies might not be missing, just dismantled. Galactic tides and collisions could have torn them apart, their stars scattered into faint streams like those found winding through the Milky Way's halo. If true, their ionizing photons weren't lost, just released in a burst before the demolition crews arrived. The paradox cuts to the heart of cosmology's biggest uncertainties. Every faint dwarf we spot or fail to spot reshapes the story of how the universe lit up. Were satellites the unsung heroes of reionization, or mere bystanders to a revolution led by giants? Until we solve this cosmic census crisis, the full cast of characters in the universe's origin story remains frustratingly incomplete. The ultraviolet background of the reionization era should have been a steady cosmic glow, a diffuse ocean of radiation left behind as starlight and quasars ionized the hydrogen fog. Instead, astronomers have stumbled onto something far stranger. This primordial UV light flickers wildly across the sky, its intensity jumping tenfold from one region to another. It's as if the early universe was lit by a string of faulty bulbs, some blazing bright while others barely shone at all. This isn't just a quirk of the data, it's a direct challenge to our models of how light permeated the cosmos during its most transformative epoch. One leading suspect, clumpy hydrogen gas. Picture the universe's neutral regions not as a uniform fog, but as a labyrinth of dense clouds and rarefied voids. Radiation passing through would face a cosmic obstacle course, some photons slamming into thick gas walls and getting absorbed, others slipping through thin patches unscathed. The result, a patchwork of light and shadow, where UV intensity depended less on the brightness of distant sources and more on the random luck of what stood in the way. Simulations show this effect could amplify natural variations in the UV background, turning subtle differences into stark contrasts. Yet when astronomers compare these models to quasar absorption lines, the fingerprints of ancient hydrogen, the observed fluctuations are still more extreme than physics seems to allow. Then there's the rogue galaxy theory. Most models assume UV light came from countless modest sources, their combined glow smoothing out into a steady average. But what if a handful of ultraluminous outliers, rare, hyper-bright galaxies or quasars dominated entire regions? Imagine lighting a warehouse with a few industrial spotlights instead of hundreds of candles. The illumination would be harshly uneven, with dazzling bright spots and deep shadows. The James Webb Space Telescope has spotted a few such candidates, galaxies from this era burning with unnatural ferocity, possibly fueled by freakishly efficient star formation or voracious central black holes. If these monsters were clustered unevenly, their concentrated fury could explain the UV background's jagged peaks and valleys. But the plot thickens when you consider time. Ultraviolet fluctuations aren't just spatial, they vary across epochs too. Some cosmic volumes appear to have dimmed and brightened multiple times during reionization, as if lights were flickering on and off. One explanation invokes galactic duty cycles, periods when starbursts or quasar eruptions flooded space with UV, followed by lulls as gas supplies ran low. Another wild possibility, the cosmic web itself acted as a funhouse mirror, with dense filaments focusing radiation in some directions while leaving others in twilight. The stakes go beyond mere curiosity. These fluctuations could explain why reionization progressed so unevenly, with some regions clearing their hydrogen fog centuries ahead of others. They might even hold clues to the photon budget crisis if UV radiation was clustered rather than evenly distributed. Its overall efficiency at ionizing hydrogen could have been far higher than our global estimates suggest. Every flicker in this primordial lightscape is a message from the universe's adolescence waiting to be decoded, and as telescopes grow sharper, we're finally starting to read between the lines. At the edge of the observable universe, quasars burning at redshift 7 and beyond defy expectations. They shouldn't be this bright this soon. These monsters, powered by supermassive black holes gulping down cosmic gas, shine with a brilliance that outshines entire galaxies. Yet their light travels to us through vast stretches of what should have been neutral hydrogen, the remnants of the cosmic dark ages. Instead, their spectra reveal a startling truth. The gas around them is already fully ionized, as if someone flipped a switch long before the universe's scheduled awakening. This anomaly throws a wrench into the standard reionization timeline. If most of the cosmos was still shrouded in hydrogen fog at these redshifts, How did these quasars carve out such pristine bubbles of ionized space? One possibility is that we're seeing cosmic outliers, regions where galaxy formation kicked into overdrive early, generating enough ultraviolet light to clear their surroundings ahead of schedule. Imagine a single street lamp blazing in a pre-dawn town. These quasars might be those rare early risers, their neighborhoods lit while the rest of the universe still slept. But there's a thornier interpretation. What if reionization wasn't a single, unified event, but a haphazard mosaic of local transformations? Some corners of the cosmos may have cleared their hydrogen fog hundreds of millions of years before others, creating a patchwork of ionized zones where quasars could shine unobstructed. The James Webb Space Telescope has spotted galaxies at similarly absurd redshifts that look suspiciously mature, their evolved structures hinting at earlier star formation than models predict. If galaxies ignited sooner in these pockets, their collective starlight could have pre-ionized the gas, giving quasars a head start. Then there's the black hole growth paradox. For a quasar to reach supermassive status by redshift 7, its seed must have formed impossibly early, perhaps a direct collapse black hole, born from the collapse of a primordial gas cloud without ever becoming a proper star. These cosmic shortcuts could have jump-started quasar activity in select regions, their radiation punching through the local hydrogen before the broader universe caught up. Yet even this theory strains credibility. Direct collapse black holes remain theoretical, and their formation requires conditions so precise they'd be vanishingly rare. The plot twists further when you consider feedback. Quasars don't just illuminate their surroundings, they blast them with jets and winds, heating gas to millions of degrees and stifling further star formation. If these outbursts occurred early enough, they might have locked their host regions into a bizarre limbo, ionized but sterile, with quasars as the sole beacons in a landscape too agitated to birth new galaxies. It's a cosmic catch-22. The very energy that cleared the fog also prevented the growth of other ionizing sources. So are these late-blooming quasars cosmic rule breakers, or do they hint at a deeper complexity in reionization's script? The answer might lie in their shadows. As their light pierces the intergalactic medium, it casts spectral shadows where surviving neutral hydrogen absorbs specific wavelengths. By mapping these absorption lines, astronomers can reconstruct the ionization state of the gas along the line of sight, and early results suggest a maddening inconsistency. Some quasars show nearly complete ionization out to vast distances, while others reveal stubborn pockets of lingering fog. This inconsistency is the real enigma. If reionization were a uniform process, these variations wouldn't exist. Instead, we're left with a cosmic jigsaw where the pieces don't quite fit, a universe that flickered to life unevenly, its brightest monsters shining through gaps in a curtain that hadn't fully lifted. Until we find more of these extreme quasars or uncover the hidden forces that let them flourish so early, their existence will remain one of reionization's most tantalizing loose threads. Even after the grand fireworks of reionization, the universe held onto a few stubborn secrets, tiny pockets of hydrogen that refused to surrender their electrons. These last holdouts, making up barely 1% of the original cosmic fog, cling to neutrality like survivors of a forgotten age. But where did they hide? The answer might lie in the loneliest places in existence's cosmic voids, or in gas so dense it outmaneuvered the very radiation meant to destroy it. Picture the voids, vast, bubble-like regions of space nearly empty of galaxies, stretching hundreds of millions of light-years across. In these desolate expanses, the sparse hydrogen atoms were too far from any ultraviolet source to be fully ionized. Like a shadow in a desert, they lingered, untouched by the radiation flooding the brighter, galaxy-rich filaments of the cosmic web. But voids alone can't explain everything. Some of this surviving neutral hydrogen is found suspiciously close to active galaxies, places where ionizing photons should have been abundant. That's where self-recombining gas enters the story. In dense galactic halos or collapsing protostructures, hydrogen gas could have pulled off a cosmic sleight of hand. When ionized, the gas sometimes cooled and recombined faster than new photons could strike, like a curtain closing between lightning flashes. These self-recombining regions created fleeting neutral zones, flickering in and out of existence like shadows in a strobe light. Over time, the densest pockets might have stabilized, forming persistent islands of neutrality in an otherwise ionized sea. Today, we see their fingerprints as Lyman limit systems, clouds of gas so thick they completely absorb light at the specific wavelength hydrogen loves most. These cosmic roadblocks observed in quasar spectra act like cosmic speed bumps for ultraviolet photons. Some might be the last remnants of reionization's unfinished business, while others could be newer structures born from recycled gas. The James Webb Space Telescope is now spotting these systems in unprecedented detail, revealing a surprising truth: the universe never fully cleaned its slate. What's astonishing is how these holdouts shape the cosmos even now. Their presence influences how light travels across billions of years, subtly distorting the signals we use to map the universe's history. They might even hold clues to an even deeper mystery: whether reionization truly ended, or if, in some quiet corners of the cosmos, it's still flickering on like an old bulb refusing to burn out. What began as a simple question, how did the universe wake from its dark ages, has spiraled into 25 interwoven enigmas, each more perplexing than the last. The hunt for population 3 stars, the uneven bubbles of ionization, the missing photons, the ghostly whispers in the 21-centimeter line, these aren't isolated curiosities. They're threads in cosmology's grandest tapestry, a story still being woven where every answer unravels 3 new questions. The Cosmic Reionization Era refuses to fit into tidy models because the universe, it seems, enjoys chaos as much as we crave order. Consider how these puzzles lock together. The scarcity of early quasars ties directly to the photon budget crisis, which links to the patchiness of hydrogen's disappearance, which circles back to whether dark matter's invisible hands guided the whole process. Even the local groups, dwarf galaxies, those fossilized relics, hold clues to why reionization's timeline wobbles across the sky. It's a cosmic Rorschach test where every observation reveals another layer of complexity. Yet for the first time in history, we have tools to crack this code. The James Webb Space Telescope peers deeper into infrared than ever before, spotting galaxies so faint they redefine what's possible in the early universe. Soon, the square-kilometer array will map the 21-centimeter signal in unprecedented detail, tracing hydrogen's ebb and flow like a cosmic tide chart. And lurking on the horizon are next-generation instruments like the Roman Space Telescope and ELT, poised to dissect reionization's spectral fingerprints with surgical precision. What's thrilling isn't just the potential answers, it's the certainty of surprises. Every time humanity builds a better window into the past, the universe hands us a fresh paradox. Perhaps JWST will find those mythical population 3 stars, or maybe it'll uncover something entirely unexpected that rewrites the script. The SKA might detect dark matter's imprint in the hydrogen forest, or stumble upon a radio whisper from an unknown process. That's the true beauty of this epoch. It's not a solved puzzle gathering dust, but a living mystery, one that keeps astronomers humble and curious in equal measure. So as we stand on the brink of these discoveries, let's savor the questions as much as the answers. Which of these 25 mysteries grabs your imagination? Do you think primordial black holes seeded reionization, or was it a chorus of dim galaxies we've yet to find? Drop your wildest theories below, because in this golden age of cosmic exploration, even the boldest ideas might one day shine as bright as those first stars.